Okay, definition of linearly independent. We say if A1V1 plus A2V2 da 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 AN Vn equal to 0 can only hold when A1 equals to 0, A2 equals to 0, da da da, AN equals to 0. We say the list V1 through Vn is linearly independent. Okay, what's an obvious definition of linearly dependent then? If it's not linearly dependent, then it's linearly dependent, right?
Mhm.
But what that means is if A1 V1 plus da 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 AN Vn equal to 0 with at least one of AK being non-zero, then we say V1 through Vn, this list here is linearly dependent. Okay, so let's think about some examples. Number one, what if you have just zero vector itself? So a single list of just zero vector. Is this linearly independent list or a dependent list? Well, think about this. If you have a zero vector, you multiply something, what do you get?
0, 0.
You get 0. Does this A1 have to be 0?
No.
No. So which is it? This one, right? Dependent. So since you can choose A1 to be non-zero, you have this case where you don't have a sum, you just have, none of this exists, you just have a single thing, and that's equal to 0. So this is linearly dependent. Okay. Number two, what if you have two vectors let's say UV in the same space is linearly independent if and only if neither is a multiple of the other. Let me try to explain this by taking a further example. So, e.g., let's think about 1, 2, 1, and 3, 6, 3. Is one the multiple of the other? Okay. So what's the relationship? You multiply 3 to this guy, you get the other, right? So you have 3 times 1, 2, 1 equals to 3, 6, 3. But if this is true, you can move this to this other side and you can rewrite 3 times 1, 2, 1 plus negative 1 times 3, 6, 3. And if you compute this, you get 0, 0, 0. But wait, this looks like A1 times V1 plus A2 times V2. That's, if I call this one as V1, that as V2, and I call 3 as A1 and negative 1 as A2, the left side looks exactly like this, right? And it is equal to the 0 vector. Okay, so this looks exactly like these, right? But I also see that A1, A2 are, neither one of them are 0. So it satisfies this condition, right? So that means these two vectors are linearly dependent. So this here means these are linearly dependent. And that's why if one is the multiple of the other, you can always move one to the other side, and that just says that the two vectors are linearly dependent. So that's why this comment makes sense. Now later on, we are going to talk about basis. So we need to talk about the standard basis in Rn. So E1 equals to 1, 0, 0, da da da, 0. E2 equals to 0. E2 equals to 0, 1, 0, da da da. En equals to 0, 0, and then 0, 1. Are linearly independent in Fn. So, in other words, it could be Rn or Cn. In either case, the standard unit vectors are linearly independent. Now, why is that? It's not hard to see. You just multiply A1 times E1, A2 times E2, and so proof would be you do A1 times E1, A2 times E2, da da da, AN times EN, and you stick in these into here and do the actual calculation, you see that this thing becomes A1, comma, A2, comma, da da da, AN. Okay. So, and for this to equal to 0, the only way you can have the 0 vector equal to this is when individually all of these are 0, right? So we need A1 equal to 0, A2 equals to 0, so on and so on. So that means it's linearly independent. I forgot to mention, like earlier in this semester, I explained what linear independence means in Rn, right? Why do we say the word independence or dependence? Can you tell me why we say dependence for linear dependence. Why do we use that word? We say we're dependent, I'm dependent on coffee. That's the English word, right? So if we have like three vectors, v1, v2, v3, and we say these three, this list is dependent, linearly dependent, what does that mean?
They need each other to fulfill a condition.
One can be expressed as the other two. So there is at least one of these vectors. So linear dependence means at least one of these vectors can be represented as linear combination of the other. So something times v2 plus something times. So something like this happens for at least one of them. Now, if something like this happens, then you can always bring this equation and bring it to the other side. And in fact, they do look like our definition that you raised about linear dependence, okay? Although we want linear independence, well, we'll see why later when we talk about basis. It's really linear dependence that makes more sense than linear independence. Linear independence is like the opposite of being dependent. Okay? Yeah, so in that view, you can kind of have a feel for why you say this is linearly independent. There's no way to represent this as a linear combination of other guys, right? You see that? Yeah. That's why this is linearly independent. Okay. And similarly, 1x, x squared, and then x to the n in P and F. So this is a space of polynomials of degree n or less. This is also linearly independent. And for the same exact reason. Okay, number 5. Let's say v1 equals to 1 comma negative 1 comma 0. v2 equals to 1 comma 2 comma 3. And then v3 is equal to 5 comma negative 1 comma 4. Question. Is v1, v2, v3, is this list linearly independent or dependent? I want you to think about this. I'll give you some time. Think about this question. Who's like completely lost? I don't know how to begin. Raise your hand. It's okay. Oh, so you guys have some ideas. Okay. Dylan, you know how to begin?
I was gonna write A1, V1, A2, V2, and I was like, it has to be, A1 has to be 0, because it doesn't have to be linear independent.
Well, we don't know. You should try that. Well, you're right. You just want to write down A times V1 plus B times V2 plus C times V3. Set it equal to 0. See what that equation gives you. You want to find A, B, and C that would satisfy that. Now, if you can somehow show that the only way that's possible is A and B and C all equal to 0, then you've shown that it's linearly independent. But maybe the equations that you get are degenerate and you have some freedom. In that case, you can find A and B and C that are not all zeros, in which case you show that it's linearly dependent. Okay, so that's the idea. Right? So whatever you do, you should start off by writing down A times 1, negative 1, 0 plus B times 1, 2, 3 plus C times 5, negative 1, 4, and then set it equal to 0, see what kind of equations you get. Alright, so whether a list is independent or dependent has to do with the linear combination, right? So we take A1 times V1, which is 1, negative 1, 0. A2 times V2, which is 1, 2, 3. Plus A3 times V3, which is 5, negative 1, 4. And I want to figure out for what A1, A2, A3 this becomes 0. Oh, by the way, writing down subscripts are not so easy, right? So instead of writing subscripts, let's just go with ABC. That's easier. So let's write down ABC. Okay, so we're just going to compute the scalar multiplication first, which gives you A, negative A, 0, B, 2B, 3B, 5C, negative C, 4C, equal to 0. And now we have to do the vector addition. Vector addition adds by component, right? So the x component is A, B, and 5C. Those get added. A plus B plus 5C. And then negative A plus 2B minus C for the y component. And for the z component is 0 plus 3B plus 4C. And that has to equal to the 0 vector. But although I wrote down single 0, this is 0 as a vector. It's really 0, 0, 0. And this gives us 3 equations. A plus B plus 5C equal to 0. Negative A plus 2B minus C equal to 0. And 3B plus 4C equal to 0. Now, if these 3 equations force A and B and C to all be 0, then it means this list is independent. However, if you find the solution to these 3 that's not all 0, that means this is dependent. So let's see which one it is, okay? And I guess the easiest one to do is just simply add these two. What do you get? You get 3B plus 4C equal to 0. Oh, wait a minute, that's same as this. Now, what does that mean? It means that initially you thought, oh, I have three different equations for 3 different unknowns. And in most cases, if you have three different equations for three different unknowns, you have a unique solution, right? However, once you added these two, you realize, well, this is exactly the same as this equation, so this equation, which I thought was a third equation that's different from the first two, was really not a distinct equation, it's just an outcome of these two. In other words, this one is not anything new, you only know these two. In other words, you have only two equations for three different unknowns, which means you have infinitely many solutions. See, we know that in dimension 3, an equation like this is a plane, and you have another plane. If you have two planes in dimension 3, the intersection is a line. Lines are made of infinitely many points, right? So that means there should be a non-zero solution. However, if you stop just there, that's not really 100% convincing. To be like extremely foolproof, you just want to find three values, A, B, and C, that's going to satisfy the equation, right? So how do you do that? Well, because now you know that there's a freedom, there are infinitely many, you're free to choose some values for A or B or C that makes, that will satisfy some equation. And I look at this and say, hey, if B is 4, then C has to be? -3. Okay, so I just chose one number for B that enforces C to be -3. Let's see what A should be. If I plug in 4 for B and then -3 for C, the -15, so what is C if you have this? What is A? 11, right? So you have A equals 11. So I think what's going to happen is, if I have A as 11, and you have 1, -1, 0, and then B as 4, 1, 2, 3, and then plus C as -3, 5, -1, 4, I bet this is going to give you 0. Let's see if we are right. So what do you get if you look at the x-coordinates? Well, let's write it. 11, -11, 0, 4, 8, 12, -15, +3, -12, and this is 11 plus 4 plus -15. Oh, that is 0. And -11 plus 8 plus 3, that is indeed 0. And 0 plus 12 plus -12. Yes, indeed, this is 0, 0, 0. Okay, so seeing that this is true because of this calculation, what's our conclusion? Independent or dependent? Dependent. Okay, so the answer is, since A is not 0, and A v1 plus B v2 plus C v3 is 0, you found the linear computation equal to 0 with at least one of the coefficients non-zero. That means v1, v2, v3 is linearly dependent. Okay, so that's how you solve this. But let me try to add a bit more story to what we're doing here. You can see that we played with these vectors a moment ago, right? Yeah, so we know that they both satisfy x plus y minus z equals to 0. That's what we found out. And if you try to check it here, this is also true. If you do this plus this minus 4, it does give you 0, right? So we see that all three of these vectors satisfy x plus y minus z equal to 0. Okay. So although we haven't learned what dimension is, what's the dimension of this vector space?
2.
2. How many vectors do we have?
3.
3. Therefore, can you have 3 independent directions in dimension 2? No, it's not going to happen. So if you had this insight, then even before doing this computation, you kind of know where you should be leading to. You want to show that these three vectors are linearly dependent, which means you want to find A, B, C that are not all zero, which will satisfy this equation. Right? So that's something that's actually helpful if you have to solve something like this. Right? Let me make sure it's right. Okay, so this lemma 2.21 is called linear dependence lemma in the textbook. It's a very important lemma because we are going to use this lemma repeatedly for proving other fancier stuff, okay? And it has a lot of corollaries. But before we prove this, let me first try to explain what we're doing here. So suppose you have a list that is linearly dependent. What does that mean? That means, although we had this intuitive definition, which is to say that one of the vectors is a linear combination of the other guys, right? The formal definition is not that one. Our formal definition is that there exists A1 through AN where this is equal to 0 and at least one of the AN is non-zero. That's the formal definition, right? So given that definition, if you have something that's linearly dependent, there exists some vector in this list that's in the span of the previous guys. Okay. Now, you can kind of see that this part A is almost what I'm saying, right? What is this saying? It's saying that Vj, there's a vector among here, which is in the span of previous guys. What does that mean? That means Vj is A1 times V1 plus A2 times V2, Aj minus 1 times Vj minus 1. And that really is saying that this is dependent on the other guys. That's what this means, right? Yeah. Not only that, you can then remove that vector from the list. So here, this hat in here means this means deleted. Okay, so if you delete this vector from the list and take the span, it gives you the same thing. So in other words, there's nothing lost here. Okay. Now, if you think about this lemma from our previous context, we had an example that we just did, which is like 1 comma, negative 1 comma 0, and then 1, 2, 3, and then 5, negative 1, 4. So we found out that these three vectors are linearly dependent, right? We already have seen that this spans the entire hyperplane, which is x plus y minus z, right? Equal to 0. That was the vector space that contains these two, and these two just spans the entire thing, right? So span of these three vectors is this, because they all satisfy this equation, right? But in that case, we could delete this and still get the same vector, right? Yeah. Why are we interested in this? Well, we're interested in such a lemma because what we're really interested in is to find the basis for any given vector space. Okay, so we have a vector space, and we want to find some basis for this vector space. Now, how do you find basis? Well, you just find vectors that's included in this space that will span every element in here. But sometimes you might end up choosing too many, right? You want to represent any element in here and say, okay, I'll represent any element that's in this vector space. So x, y, z with this vector space can be represented as something times this plus something times this plus something times this. But the moment you say that, you're like, wait a minute, this is two-dimensional space. I chose three vectors. That's not right. I'm wasting memory if this was like something that's, you're writing a computer program to represent everything that's in here. You're wasting extra memory by using three numbers instead of two. That's not good, right? So you really want to come up with a basis. So what do? You start with a spanning set, and you keep applying this lemma and say, oh, look, there must be one thing that you can, at least one element you can delete. Oh, I see that this can be deleted. Let's delete. Does it still work? Yes, it does. Now you look at this. Is this still dependent? Well, no. This time it's linearly independent. If it's linearly independent, then you can't use this, and you kind of know that this will be the basis. You can't go any smaller than this. Okay? So that's really the reason behind this linear dependence lemma. All right? You need to have the intuition. Okay? But intuition and proofs are not always the same, because the proof of this, I would say, is highly technical. So even if you understood what I said and you have the intuition, it's kind of natural for you to have a hard time actually doing a proof on your own, and even following the proof itself might be hard too. Okay, so let me try to show you this proof. So step one, what you do is, since at least one of A1, A2, AN is non-zero, we choose non-zero with A1 V1 plus A2 V2 plus A and Vn equals to 0. Right? Being dependent means that there's at least one non-zero element in here such that that's true, right? Okay. So since that's true, we choose AJ to be the non-zero element, element or coefficient with the highest j. Now what does that mean? That means aj plus k, what, so in other words, aj plus 1, if j is not n, then aj plus 1 will be 0, right? Because if this is non-zero, then this will be the higher one, okay? So everything on the right side of it would be 0. That's what it means. Okay, so let's now see what that means. That means that you have a1 v1 plus da 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 aj vj plus, because everything afterwards are 0, you have 0 vj plus 1, 0 vn. All of these are 0, right? It's still equal to 0. Now what if j itself is n? Well, in that case you don't have this, and that's fine, okay? You could have some of these or not. It's just that j is the highest one, that such that everything that's on the right side, if there are any, it should be 0, okay? Okay, and then now move everything else to the other side, to the other side of the equation, so that you have aj vj equals to negative a1 v1 minus a2 v2 da 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 aj minus 1 vj minus 1. Okay, so everything before has been moved to the other side. This is 0, so they don't exist. On the left side, this is the only term that's left on the left side. And then you divide by aj. And remember, aj is non-zero, so you can divide by aj. So this still makes sense. But now look at this. This is some number. This is some number times v1 plus another number times v2 plus another number times vj minus 1. And these are the elements that are in the span, right? So this shows that this is in the span of v1 through vj minus 1. Good? And then, so that proves part A, okay? And then to show part B, to show that two sets are equal, how do you show two sets are equal?
They're subsetting each other.
Yeah, to show that if A and B are sets, to show that A and B are equal, you say A is a subset of B, and B is also a subset of A. Okay, you show two-direction inclusion, that's how you do it. Now, if I say this is A and that's B, which one is trivial? So, is A includes B trivial, or B, A a subset of B trivial? Which one's trivial?
A subset B.
No, A includes B. This is trivial. Why is that? Because anything that's spanned by this with this missing can be thought as something that's in here, right?
Sure.
Yeah, so that part is trivial. So I'm going to say that the inclusion this way is trivial. All right, if you didn't get what I said, let me just say this again. What are the elements in here? This is A1 V1 plus A2 V2 plus da da da, and AJ VJ, that's excluded, plus da da da, AN VJ, AN VN, right? But that's like this AJ being 0 times VJ. That's what this is, right? But that's exactly one of the elements in here, with this being 0. So anything in here is an element in here. That means this is a subset of this other guy. Okay. So that part is trivial. Now to show the other direction inclusion, to show this other inclusion, you show that by taking any element in here and saying that that's a subset of this guy, right? So to show this, we take A1 V1 plus da da da, AJ VJ plus da da da, AN VN in the span of V1 through Vn. Okay. But then, now replace Vj as this guy, negative A1, AJ, V1, da da da, plus negative AJ minus 1 over AJ, Vj minus 1. Okay, so if you replace this by this, and then you expand and collect likewise terms, then you end up with another linear combination that has all of these except for this guy. This is gone because you represented this by things of this linear combination of the previous guys. Right? This has been written as linear combination of previous guys, so therefore, yeah, I don't have any room to write it, but if you plug this in here and then you can say then V1 now has this plus this as its coefficient, right? And then V2 now has A2 plus negative A2 over AJ, V2 as the coefficient, right? So just keep going and rewrite that, and that is indeed, that's it. Yeah, if you do that, then the other inclusion is proved. So QED. So if you put a square with darkened in thing, that means the proof is done. Okay. Okay. So what are some corollaries? This is a very powerful theorem. So let me show you some corollaries of this. Okay, so this is our first corollary of the linear dependence lemma, 2.21. So I'm going to refer to 2.21 many times in this lecture, right? Linear dependence lemma. Okay, so the theorem is that the length of independent list is less or equal to length of the spanning list, length of a spanning list. And by this, the real conditions are this. Suppose V1 through Vm is linearly independent in V, so that it's a linearly independent set, linearly independent list, and V is equal to span of W1, W2, Wn. Okay, notice that M and N are different. Okay? So M is the length of the linearly independent list, and N is the length of the list of vectors that span the whole vector space. Okay? Now, to span a vector space, we actually have some intuition, right? So if V is three-dimensional, at least how many vectors do we need to span it? Three, right? Okay. Now, if V is three-dimensional, can you have four vectors that are linearly independent? No, three-dimensional vector space can afford only three distinct directions, right? The moment you add the fourth vector, that fourth vector will be representable in linear combination of the other three. So that's the intuition behind it, but that's just intuition, right? What we're trying to do is to actually formalize what we just said in terms of intuition and prove it because we had laid careful foundations for what a vector space is, what a span is, and all that, okay? What linear independence is, and all that. All of that has been formally defined, and now we're able to prove such a statement, okay? Not just have intuition for it. Okay, so these are the conditions. So if these are the conditions, then m is less or equal to n. Okay? So let's try to prove this. Proof. So because V1 is in V, which is the span of W1 through Wn, that means V1 is some linear combination right? Being in the span, that's what it means. But then if you move everything to the left side, you have 1 times this plus negative A1, W1, and so on equal to 0. That means that there is a non-zero coefficient which will make the linear combination of these to be 0. So in other words, this means that V1, W1, W2, Wn, right, is linearly dependent. Okay, so I took the first element, attached it in here, and this is now linearly dependent. But then, what we know is that V1, W1, W2, Wj taken out you can take out one of the elements and still have the span to be same as before, which is V, right? Oh, I forgot to say, what's the span of this guy? Well, span of this guy is bigger than span of this guy because you have more elements than here, right? But this is already giving you the entire vector space. So this will give you the entire vector space. But then, because of the linear dependence lemma, so I should really say by 2.21 linear dependence lemma, you can take out something, and the span is still the same. So what happened? What's the new length? Well, this is length n. Do you agree? What's this length? What's this length? How many do you see? N plus 1, right? But then you took 1 out. How many do you see? N. Because n plus 1 minus 1 is n. So this is still length n. And now we're back at back to the same situation. We have a spanning set. This is still a spanning set, right? So you can repeat this procedure again. Take something out. But this time you add V2. So now V1, V2, W1 with Wj taken out is linearly dependent again. Okay, for the same reason. Every time you take something in, n plus 1 is the length, and you take something out by applying linear independence lemma. And by 2.21 again, there's Wk that's taken out. And still gives you the same spanning set. And because that can be done until you run out of all the vectors here, right? Yeah. Because there's nothing in this algorithm that prohibits you from taking an element and attaching it and taking something out, right? So since this can be done indefinitely, I'm missing a crucial argument here. Why can't this next one be V2?
V1 is linearly independent?
Yeah, because, see, the linear dependence lemma says whatever you take this, that chosen one should be the linear combination of previous guys, but if V2 were to be chosen, that would mean that V2 is a linear combination of this guy. So, but we know that the condition is this is linearly independent, right? So, note that V1, V2 cannot be Wk since V1, V2 are linearly independent. And the choice of part A of 2.21 says Wk, V1, V2, Wk is linearly dependent. Okay, since Wk is a linear combination of previous guys, this list is linearly dependent. So it can't be, the list can't be one of these, right? So that means because this logic holds indefinitely until you run out of VMs, at the end of the day, what you end up with is V1, V2, all the VMs will be attached, and you should still have some WK left out, or maybe there might be none of WK, but you should be able to do this. So, we see that M has to be less or equals to N. Okay? So now, we can go back to that same question we had before, number 5. 1, -1, so is linearly independent or dependent? Well, we had a previous question that we solved, right? So solution using that is that we know we showed before that span of 1, negative 1, 0, 1, 2, 3 is equal to this hyperplane. Okay. And it's just and 5, negative 1, 4 is also, let's call this V, in V. Right? So we know that they all lie in that same vector space, right? So if one, two, three, 5, negative 1, 4 is linearly independent, then its length is what? What's the length of this linearly independent list? How many vectors do you see? 3. Right? But what's the length of the spanning list? 2. So we have 3 less or equals to 2, because we have 2 of them. That's a contradiction, right? So we can show that the moment you show that the span of this is equal to that, and showing that this is in V, then you can indirectly show that it can't happen. This must be linearly dependent. Okay, so that's one thing. Well, another simpler example is question. Is 1, 1, 2, 1, 1, 3, 1, 1, 4, and 1, 1, 5 linearly independent or dependent? Well, they are all in dimension what? R3, right? So in R3, we know that R3 is spanned by what vectors?
3 vectors.
So R3 is span of 1, 0, 0, 0, 1, 0, 0, 0, 1, right? Isn't that right? R3. So that the length of the spanning list is 3. That means, can you have length 4 linearly independent list? No. Since length of spanning list is 3, which is what we just saw, it is impossible to have a length 4 linearly independent list. So that means it's linearly dependent. So that's like an indirect way of showing that these 4 vectors must be linearly dependent. Okay? prove this without looking at the textbook and realized that I made a fine mistake. So let me look at this again because it almost seems trivial, but it's not. Right, okay. So, okay, so in this class, we are not going to be dealing with infinite dimensional vector spaces. Really, the focus is going towards the Jordan normal form. So, and Jordan normal form is really finite dimensional, so we're not going to go there. But this is still important. To be able to define what the dimension of a finite dimensional vector space is, you want this obvious thing to be true. Any subspace of a finite dimensional vector space is finite dimensional. So how do you prove it? Okay, proof. Let's say U is a subspace of V, where V is a span of say U1, U2, UN. Because that's our definition of being a finite dimensional space, right? If you can write a vector space as a span of finitely many vectors, that means it's a finite dimensional space, okay? All right, so if we're going to do it by induction, so by induction, if U is just a trivial subspace, then U is finite dimensional. U is equal to span of the empty space, right? That was our convention, right? So the span of empty space is the trivial space, and so it is finite dimensional. And U is finite dimensional. And now if it's not just 0, then we can keep doing the following procedure. Suppose U is infinite dimensional. Okay, suppose not. We're trying to come up with a contradiction. Then, if V1 through Vk is in U, and these form a linearly independent list, then since U is not equals the span of V1 through Vk, why not? Because if it is equal, then it'll be finite dimensional, right? But we're trying to come up with a contradiction if it's infinite dimensional. We can find Vk plus 1 that's not in span of V1 through Vk. Okay. Then V1, V2, Vk, and then Vk plus 1 is again linearly independent, right? We know that these are linearly independent and this is not in the span of this. So it's linearly independent. If it's dependent, then it will be contradicting our linear dependence lemma. So if this entire thing is dependent, then one of these is in the span of the previous one, but the way we're constructing it is always that the next one is not in the span of the previous one. So this is really by, again, 2.21, linear dependence, right? But then this means, so at some point, we have V1 through Vm linearly independent because this can keep going, right? By induction, it can keep going, right? So at some point we have V1 through Vm linearly independent, and that m would be bigger than n, right? With m bigger than n. But you have a linearly independent list that's bigger than the length of the spanning list, right? So that's a contradiction. That contradiction proves that this must be finite.